So useful ignorance, why we don't really understand what machine learning models are doing. Like I say, why I said he's heard that machine learning models are a black box, and there's a part of the black box is because it's doing a lot of I'd say confusing maths, maybe not, or maybe complicated maths that people will say, hey, it's just a black box and it's doing some stuff I don't really quite understand if you haven't actually gone through a course. But I'm actually going beyond that. I'm going to say that that even when we understand what the maths are doing, the output, we cannot predict what it's going to output, and we can't really explain why. When the output is bad, we can't go back and look at the model and say, well, this is bad because of X or Y, and now we're going to fix that. Instead, we just train it with more data, right? So we don't really understand why it does what it's going to do. Right now, Harsh, what do you see on the screen? What is that?
6.
It's a 6. Okay, good. It's good. It's a 6.
It's a skunk with a tail.
Okay, that's great. But it's a 6. Like, who here recognized that as a 6? Anybody not recognize? Did you actually recognize it as a skunk with a tail? No.
I could see it as a G, maybe.
A G, yeah, maybe. Contextually, right? If I said this is a number, immediately you'd say, because there's something going on in your brain, right? Why, Harsh? Why is that a 6? Like, what? If I were going to ask you to tell me the features of that 6 that make it a 6, what would you tell me?
Just like this.
Yeah.
So G is also a candidate, but the G's that I know has like a little extended middle line.
Okay. So from your memory, you're remembering that G's are different, but outside of it not being a G, why is it a 6? What about this makes it a 6?
A spiral figure that closes towards inside.
Okay, so a spiral figure that closes towards the inside on the bottom?
Anywhere below the middle.
Okay, anywhere below the middle, right? Anybody else want to tell me what features they see in this that would also make it a 6? Because I got my own definition, and I'll show that in a minute, but I'm just curious.
Pretty good.
It's a good one, okay. I have my own, so I'll show you my own. Highly technical language here. First, we have a circular loopy bottom, right? Highly technical language. And then we have a bendy top line. That's what I'm describing. That's how I would say it. I'd say, this is, if somebody were to tell me, why is this a 6 and why is it not a 5? I'd say, well, it's a circular loopy bottom and a bendy top line. What else is this? This is also another 6, right? Does it fit my definition? Kind of. Circular, I guess that's circular. It's not closed, not as close as that. But it also has a bendy top line, although that's more of a left line, not actually full top, but it kind of fits, right? What about this one? Now this really kind of changes our definitions, right? Because here it's not really a circle anymore.
Or bottom.
Right? Yeah. Or bottom. Yeah, I didn't even point that out, but that's a good point. So it's like we have to start modifying our definitions. This is circular-ish loopy bottom, and even the top line, it's often bendy. It's not actually, could be straight even, and we can still recognize it as a 6. So now we're having to update our own definitions of what this is. Interestingly enough, like when you all did that in your brains, when you were learning what 6s were, is this how you thought about them? No, right? What you did was you saw a bunch of 6s and your brains categorized them with characteristics that make it a 6 without you really understanding what those characteristics or what those features were that make it a 6. That's how your brain was trained, right? What about this one?
Do you call that a 6?
I don't know. Is that a 6?
I think it's a 5.
Honestly, it's a 5, right? But it actually fits kind of our definitions, right? If you had not been trained on a 5, you might think that's a 6 and then update your definitions of 6. You have to have somebody tell you that's a 6 or a 5, and you are now updating your brain, your brain categorization of what that is. That was actually a 5. I did take the top line bar across the top and I made that a little shorter just to make it fit this example, right? But it's funny, you saw it as a 5 anyway. Something in your brain has been trained. Yeah, advanced model brain, and also looked at a lot of numbers, a lot more than most of us, right? So, and so now we have to then train our brain to think, these are all 6s across the top, these are all 5s, and as we keep seeing 6s and 5s, our brain's model keeps getting updated with what is a 6 and what is a 5. And of course, if we want to train for all numbers, then we have to train for a bunch of different inputs, 0s, 1s, 2s, and because we're going to classify this is going to be our specific classification function for whatever the numbers are. And the way you would do this, all right, so that's how we did in our brain, right? And we didn't, like I say, we don't actually go around, like Hirsch had a slightly different feature set as to describing what a 6 is. I imagine our brains probably look very similar to what a 6 or 5 is. Just later on, we're going to describe that feature set. We're saying this is the feature set and this is how we do it, because if we're trying to train a child, for example, and they're like, well, why? And they misclassified that, and we have to say, well, no, it's not a 6. Well, why? Well, because it doesn't have the loopy bendy thing, right? Or it doesn't have the bendy line, or it doesn't have whatever feature we're making up after the fact. We're saying these are our features. They actually aren't the features that our brain have recognized. Our brains have recognized them because of how we train them. But later on, we're giving meaning to them and trying to find features so we can explain it to other people, right? It's actually much better for us just to see a bunch of 6s and say, that's a 6, that's a 6, that's a 6, that's a 6, and then our brains adjust appropriately. So if we were going to do this with a neural network, because neural networks are loosely and roughly based off of the neurons in our brain and how our brain stores information, very loosely and very roughly, but that was the inspiration of this kind of concept. So if we're going to do that, let's say this is a small number, each of these squares are a pixel. We would then classify in a neural network, we would take the 6, and we would, for each input neuron, we'd have a value that represents the color inside each of those pixels. So this would be color, I always forget, I guess that would be color 255, right? Black is 255, right? Yeah. White is 0. I always get mixed up, right? White is 0, black, white is absence of color, right?
White's 255.
Yeah, that always confuses me. That's why I get messed up, because if you think about it, I guess white is all colors in the real spectrum.
Depends on if you're talking about light or pigments.
Yeah,
Light,
I always think of light.
light
I don't
adds
think
up
pigments.
to white.
I thought white was 255, black was 0.
Yeah, I always get it mixed up because white. Yeah. Anyway, that's where we're at. So you would have 0 then, pixel 1, and then these other ones you can see some of them are gray, and you would actually fill out all of those for the neurons. Now the hidden layer, what's known as the hidden layer, over here, and we'll get a little bit more detail into that. This can be selected for whatever size you want it to be. It can be 16, it can be 50. It doesn't have to match that 784 inputs. It just it gets trained. That's actually where the training is on that layer. And you can have multiple layers, but we won't talk so much about that. Right, but this is what you would do in this. For us to recognize this, we would put a color in there. And then, as you can see, we have a 15 neuron hidden layer here, 784 neurons here, and then of course, ultimately we want the output to be 0, 0, or 9. How does that work? So this is a very simplified, small neural network. This is the input layer, IL1 and IL2. Hidden layers 1, 2, and 3. Each line, so what, as you saw back here, we were drawing lines from each of the neurons, each of the input neurons to each of the hidden layer neurons, the second layer of hidden layer neurons, so forth and so on. You keep doing that. Each of those lines has a weight associated with it. And each neuron has a bias. So I would say it's more like an input bias. There's a bias that happens to the neuron. And then you have an activation function. So in order to go from input layer 1 and input layer 2 to hidden layer 1, you would take the value of input layer 1, you would multiply it by a weight, and then you would add the value of input layer 2 and multiply it by the weight attached to the line there. And then after you have that sum, the weighted sum, you would actually add all those together. You then add a bias. What should those weights and biases be? That's all part of the training. And I'm not going to go into detail about that. Maybe in a later presentation I will. But it's all part of the training. You've trained it to have the biases, the weights, have a certain number attached to them. That is what we refer to as parameters in a neural network. So when you hear people talk about parameters in a neural network, the parameters are the weights and the biases. That's what the parameters are. There's also hyperparameters, but that's part of the training. It's different. The parameters are weights and biases, and the larger your neural network is, the more layers you have, the more parameters that you have, more weights and biases that you have, right? And so ultimately, what it comes down to, when you go through the training of this simple neural network, and when I say you train it, there's this whole back propagation thing again. Maybe we'll talk about that later. But just know that ultimately, the model is trained with values here for each of these weights and values for the biases. And so this is some random number that we have here. And so when you look at this right here, another way of looking at this right here is the feature set that the neural network has found based on the training that you gave it. Right? Before I asked you what features there were for the loopy bottom and all that, it'd be great if that's what happened. If at the end it found the loopy bottom, or it found the spiral that goes in on itself. If that's what it found and we could discern that from these numbers, then we would be able to understand. We would say, hey, this is a trained neural network, and we see why it says this is a 6. Unfortunately, what we have is a bunch of different numbers for the biases, and we have no understanding of those numbers. We don't know, we call them features. These are the features that are found, but we cannot make sense of those features ourselves, not in the same way that we can try to make sense of what our brain has done with the 6. Right? Now this is with a very small neural network, and I have actually seen people reverse engineer neural networks for very simple tasks. Right, so you can go back and try to understand what it's doing. Most recently, there was a blog post that I read. A guy trained a neural network to do binary addition. And binary addition, if you remember, like one of the tricky parts of there is when the most significant bit transfers past the 8 bits, then it disappears. It goes off. Right, and so I had to train this network this neural network to do a binary addition. And it did it with a lot less parameters than he expected to have. And he was able to reverse engineer and identify what it was actually doing. So on a very small network, you might be able to go back and to identify what it's doing. But
How many bits do you do?
what do you mean? You mean how many input?
Yeah, like, is it an 8-bit adder or a
Yeah.
4-bit adder? Is it
Yeah,
an 8-bit adder?
yeah. And he was expecting it to need at least 8 layers. It didn't need 8 layers. It needed much, much less for it to be that useful. I'll send you the blog post.
Yeah.
I thought about presenting on that today, but I decided to do this instead. Maybe that'll be another mind garden at some point. It's pretty cool. And I've seen others do something similar where they've been able to reverse engineer, but it's only if it's very small, right? If we're doing something like GPT-3, right, the parameters are 175 billion. You're never going to be able to make sense of that. And this is why when people, like I had a buddy who worked for fraud detection at Twitter. And they did a machine learning model for fraud detection at Twitter, and it was more effective than the heuristic checks that they were doing. But he said they had to stop using it. And I said, if it's more effective, why'd you have to stop using it? He said, because we would detect somebody as fraud, and they would ask, why are you detecting me as fraud? And the only thing we could say is, because the machine told us to. Right? You can't give you, what is it about me that looks like fraud? I don't know. It misclassified. All we can do is just use that to retrain our model, and hopefully it'll eventually get better and not detect whatever characteristics you are. Right? Now, this is contradistinction to, if you remember, some of y'all will remember this, or maybe you won't, but early on, a while back, I did a Mind Garden presentation, Intro to Machine Learning, where I was talked about genetic algorithms. And like I say, this is in contradistinction. One of the examples I used there was a very simple genetic algorithm that was a robot picking up cans. And let me refresh your memory, or let me explain it to y'all. Let's say that we have a robot that has a very small amount of memory and very small vision. It can see, it's in a grid, and it can see what it's on its square. All the green is the areas that it can see around. And what we want to do is we want to have an algorithm that will efficiently be able to pick up the cans with the least amount of moves. Each can is a fitness function or reward function, right? You pick up a can, it has a score, and at the end you score it, right? And so naively, you would sit there and say, if I'm sitting on a can, I want to pick up a can, right? Because that gives me 10 points. That's what's happening. The neural network also, or the genetic algorithm, would also penalize if you run into a wall. And so you think you could program in to say never run into a wall, but you wanted to evolve that, right? And so you pick up a can, and then now you can see to the left and to the right, so you can go left or to the down and to the right. So you can go right or you can go down. So you go right, and you pick up that can, and then you go right, pick up that can, and then you go up or down, so we go up, and we pick up that can. Now at this stage, we've lost all contextual information. Now we're just randomly guessing about where we should go in order to pick up the rest of the cans. Because while we saw them before, we have a very small amount of memory. We couldn't do that. And when I first did this, with the genetic algorithm, I actually found an implementation online because I'm lazy and I didn't want to implement it myself. And so I found one online that was not as effective as it should have been. And when I looked into the code, I found out it's because they were trying to cheat doing this kind of thing. They actually didn't let it evolve. Instead, they said, well, let's short circuit it and pick up a can because we want to get as many points as we can immediately. Let's do that. When I took that line out and I had it run, the genetic algorithm found this was a better move. Right? Did not pick up the can, it just moved right or down. It then moved again, did not pick up the can. It moved again and did not pick up the can. And this whole time I'm like, well, why is it doing this? With this kind of algorithm where we have very simple parameters, we can understand. We can go further and say, it picks up the can here. Why did it do that? Well, because now it has a breadcrumb trail. It now knows it can look below, go down, pick up that can, or not pick up that can, leave it there, because it goes back down, picks up that can, goes up, picks up that can, and now it's actually doing this breadcrumb trail where it ends up picking up, it's more effective to leave that breadcrumb trail. So ultimately what the algorithm did was it showed that if you were on a can and there was more than one can adjacent, then leave that can so you would actually leave the breadcrumb trail. Wasn't obvious, but that's something we can understand. With these 175 billion parameter neural networks, we can't have that kind of understanding. It quite literally is, we don't know why this happened. The algorithm told us to. And you actually get that a lot when you try to interact with these large companies, either through fraud or maybe they detected your email as spam or whatever. It's like, well, it's because the computer told us, we'll just retrain it. We'll just use that to train it more. And it even has even broader implications. The first time I started thinking about this presentation was when I saw a tweet by somebody who said, every once in a while I think that we have a machine learning model that can take an image of an iris and detect quite accurately if that belongs to a biological male or a biological female. And yet we don't know why. That's a reality. This happened, there was a lot of this kind of research being done in 2014, 2015. Anybody care to guess? Biological male or biological female?
Looks like there's no makeup on the eyelids, I'm gonna say male.
Okay, biological male right here. I'm going to say you are 50% accurate. It's either male or female. I don't even know, right? The point is, the best you can do is 50% accurate. But not only the best you can do, they've actually, as they were doing this flurry of research, they had ophthalmologists as their control group to try to identify if it was male or female, and they were as accurate as you were. They were 50% accurate. The latest one I saw was 91% accurate. And it's because ophthalmologists, people who are expert at eyes, we don't know, like, what is different between a biological male and a biological female that are showing up in the iris. We have no clue. No idea. We have no way of finding it out either, because these neural networks are way too complicated. We just know that it is, and that's it. So anyway, that's why we don't understand. We don't really understand what machine learning models are doing. Yeah, why?
I can't remember where I heard this. I can't back it up, but I heard somewhere that somebody said that our brains can be trained in a similar way, where we can recognize things without knowing why. And they used an example. Now I'm pulling from old memory here, so I could be way off.
Mhm.
But I'm pretty sure it had to do with these people that had to sort eggs. And they were, I don't know if it was a study or what, but they were like given positive reinforcement if they were able to guess the gender correctly for the egg for like a chick or something. And they had no idea really like what they were basing it off of, but eventually they were able to train above 50% their own brain to be able to pick out whether or not an egg was a female or a male, not knowing why, but just because they had enough positive reinforcement that their brain was able to train on it.
Interesting. So they can't tell you what features they're doing in their brain.
Right.
It wouldn't surprise me too much. I know that one thing. So most recently, I came across, there's a book I read. I came across an example. I think it's very difficult for us to answer why questions about our own behavior.
Yeah.
Like just in general. And I'll give you an example. This is an example. I've been thinking a lot about this lately, and I've been trying to find other examples of this kind of research. But it was in the 90s. There was a young woman who had really bad epileptic seizures. And so they were going to go in and operate on her brain in order to help stop these really bad epileptic seizures. And she was young. And this has not happened often, right? But what they did is, get this, your brain does not have pain nerves. Your brain receives pain signals. It does not have pain nerves. And so what they did was they drilled several holes in her head in different places. And she was awake after they drilled the holes, and they then took electrical probes and put them into her brain where those holes were, and they would then trigger a small electrical charge and then ask her what she was experiencing, right? In order to try to identify where they should operate for this epilepsy. Yeah, sorry if this was squeamish for some of you, right? It's fascinating though, because she was awake and conscious the whole time while they were asking her this. And this is a part that really blew me away. At one point, they put a probe at one particular spot in the brain, and maybe I'll send a link to all of this as well. One particular spot, and they triggered it, and she starts laughing. And then they ask her, well, why'd you laugh? And she says, well, that painting on the wall of the horse, it's just hilarious, right? It's funny. It wasn't funny before, but now it's funny to her. She's attaching meaning to the emotion because she wants to be consistent in her brain. So this is why, and same things. Another time she did it, they did the same thing, made her laugh, and she said, why are you laughing? She goes, well, just all you guys standing around in your lab coats. It's really funny. Again, making up reasons for why she's laughing. So I think oftentimes when we ask ourselves why questions on these kind of esoteric, I don't know that we actually fully really understand that. So wouldn't surprise me too much. Any other questions, insights?
So you addressed neural networks,
Yeah.
but your presentation said ML models.
Yeah.
Do you have a similar argument for not understanding something like logistic or linear regression?
I haven't really thought about it. Do you? Can you think of one?
Well, those models are considered identifiable because you get your p value for each feature, and so you can actually say that this input led to, the predictiveness of the model. So I feel like some ML models, we actually do have a pretty good idea of what's happening, but I would agree that neural networks and things in that category, we're just doing tons of linear algebra and it's working and we're just moving on with our lives.
Yeah, that's a good point. Maybe I think my title's probably maybe more broad than it should be. Like I can give an example in here of at least a genetic algorithm where you can understand it, right? So there's certainly, it's not all machine learning models, but it's, of course, the ones, like even machine learning models, or I should say neural networks use linear regression. And I've often said that machine learning models, that you can get 90% of the way there with just linear regression on most uses, right? And then I see something like ChatGPT, and I'm like, I don't think linear regression could do that, right? So obviously there's kind of a new frontier, but yeah, it's a good point, good insight. Any other questions, insights? Great, thanks everyone.